My name is Danling Wang, and it's kind of a little confused because I graduated from the University of Washington, Seattle. The project I present today is mainly finished from the University of Washington. I just recently joined the North Dakota State University as assistant professor in the Department of Electrical and Computer Engineering. Okay, so the topic today, I'm going to present a portable breath analyzer for the diabetes. So as we can see from the National National Diabetes Status Report in 2014, there's almost 29.1 million people in US has a diabetes issue. And also the average population in US, 1.4 million US are diagnosed as diabetes almost every year. And besides this, and the pre-diabetes population is also increased, in particular for the person is younger than 20 years old. And also the cost for the diabetes usually recently use the equipment and the device costs are very high. So the main purpose for our project is to find a way or develop a new device can detect the diabetes, also doing the daily monitoring for in particular for diabetes type 1 with low cost. That's one example about the traditional diabetes detection method, monitoring method by using the blood glucose meter to finger pricking. This way is usually inconvenience and also invasive and painful, particularly for the little ones, the case. And the cost for the meter and the test strips is usually is a lot, a couple $100 usually per year. So our idea is to develop a portable device can just simply to detect the acetone or biomarker gas from breath. So something will be developed like this. This technique will be non-invasive and no painful at all. And you can detect the diabetes anytime, anywhere if you want. And the cost can be controlled during the fabrication process and the materials preparation. So that's our idea. The fundamental reason we can use the device to detect the acetone because the literature or scientists or the doctors have already investigated about there's a linear relationship about the acetone concentration in our breath with the glucose concentration in the blood. So this gives you a finger about how related each other. So that's why the acetone is a good biomarker to detect acetone in our breath. They also have found out there are 3 kinds of threshold to detect the acetone to distinguish about a diabetes person, health person, and a high-risk person. So for the diabetes person, the concentration about acetone level in our breath is larger than 1.7 parts per million. And if the threshold less than 1.76 parts per million, you can see this person will be definitely very healthy. So our device should be very sensitive, can detect the concentration in this range. Then we can distinguish the person is health or high risk or the diabetes. Also, we have to be develop a sensor device has a fast response because if you detect the breath, you cannot hold the device for a while. It should be in a minute. That's why we had developed some compared to other kind of non-invasive technique to detect acetone, such as the mass spectrometer. This type of technique is very expensive and very complicated because you have to train the specific person to operating this equipment to get the accurate data or analysis about the breath. So Before we going to detect about the mechanism of sensing of the sensing device that we developed, I want to mention about the specific chemical property of the acetone. Compared to other components in our breath, the acetone shows the highest dipole moment. What that means? It means if there's a high, some kind of material with some kind of high dipole moment can interaction effect with another high dipole moment acetone, then the sensor should be very sensitive. Then the target is to develop a new synthesize about new materials with this such kind of property like a ferroelectric property and a semiconductor, because we are doing some chemiresistive sensor. Semiconductor can give you a change about conductivity during interaction with the sensing material. And also, this material is a capability to doing the charge transfer between the sensing compound and the material. Okay, so that's a material developed in our group, in our lab. We call it just like KWO, is an easier way to call this name. And the SEM shows that the structure or morphology about this material is a nanorod, and it's a kind of porous structure. We just using like a hydrothermal method to grow up the nanorod at a different temperature, and we can see about the STEM to show this material is a single crystal nanorod. And we're using the XPS to identify the components of a different atom ratio. We found out the ratio is a K cell, and tungsten and oxygen, the ratio is 2.7.22. That's why we call this material is K2W7O22. That's a new material, has never been reported before in any of the literature so far. Then we detect if this material has a ferroelectric property, in particular in the room temperature. She just mentioned the tungsten oxide. Tungsten oxide has a very good ferroelectric property, but it generally only can exist in the limited temperature. It's a very low temperature. So this material can have the high at the room ferroelectric property. That's using the piezo ferrometer to force microscope to detect, and we can using two samples we fabricate in our lab. We found the face is have a chemiresistive face, and also there's a butterfly shape of about the amplitude. All this picture indicates the material we fabricate in our lab has a ferroelectric property, in particular at the room temperature. And we're using Hall effect measurement to test the semiconductor property. We found this material we fabricated is a p-type semiconductor and have a good mobility and conductivity. That's a kind of picture about the sensing processing. It's showing about how when the acetone interaction with the sensing material, the conductivity or resistivity will change and can be monitored by the computer. And also this just the kind of picture about the lab setup, how this sensor works. Our preliminary results show the sensitivity or detect limited based on this lab setup. It can be up to 2.0 parts per million. So it's already good to distinguish about the high-risk person and diabetes person, but not good enough for distinguish about health person and a high-risk person. That's one thing. Another thing we can see, this sensor response time is only about 12 seconds. It's fast in a minute. And the sensitivity we can show the detection with different relative humidity, and we can see with the humidity is even very high, the sensor performance still very good. So we develop a kind of material-based sensor and have a good chemiresist response, and can operate at room temperature, and also high sensitivity, can up to 2.0 parts per million so far, and fast response just within 1 minute. And we detect other kind of understanding the selectivity issue. We detect other organic compounds like ethanol and also the water. The material shows the highest response to the acetone compared to other major compounds in our breath. And we also developed a kind of prototype sensor device using some fancy electronic board to amplify the signal, and finally we can get the detect limit up to 0.025 parts per million. It's much less than 1.7 parts per million. So this sensor type can be used to distinguish health person, high-risk person, and a diabetes person. So the sensitivity is good enough already. And then finally, just kind of summary here. I compared our data and results with other sensor based on the metal oxide material. Our sensor can work at the room temperature with the highest detect limit up to 0.025 parts per million. And also the mechanism mainly based on the dipole-dipole interaction makes the charge transfer between the sensing material and the detection material, molecular. So that's a good material. So far we have investigated, and the final goal, we want to use this material to integrate on the chips to make a smartphone-based sensor device. Okay, I'm done actually. Thank you. If you have any questions, please feel free to ask.